Good day, learners. Now we are going to have the methods of simplifying radicals. So the first method states that removing perfect nth powers. In removing perfect nth powers, we need to break down the radicand into perfect and non-perfect nth powers and apply the laws on radicals. Nth root of x times y is equal to the nth root of x times the nth root of y. For example, we have the cube root of 32 m raised to 4 n raised to 32. So we need to break down the radicand into perfect and non-perfect nth powers. But first, we need to write 32 as an exponential expression. So therefore, we have the cube root of 2 raised to 5 m raised to 4 n raised to 32. So we are going to factor this in such a way that the radicand will become a perfect and non-perfect nth powers. So therefore, we have the cube root of 2 cube m cube n raised to 30 times the cube root of 2 square m raised to 1 n raised to 2. So as you can see, the first factor is a perfect nth power, while the second factor is a non-perfect nth power. Applying the laws on radicals, therefore we have 2m n raised to 10 times the cube root of 4m n squared. Next is to reduce the index to the lowest possible order. In doing this, we apply the laws on radicals. Nth root of x is equal to the mth root of the nth root of x is equal to the nth root of the mth root of x. In other words, we can interchange the indices, or we can factor the index to simplify or to reduce the index to its lowest possible order. So for example, we have the fourth root of 4. So take note, the radicand 4 could be written as a power of 2. And the index 4 could be factored in such a way that we can have the square root of the square root of 4. So therefore, we have the square root of the square root of 2 squared. So simplifying the inner radical by applying the law on radicals, therefore we have the square root of 2. Another example, we have the eighth root of 9a raised to 22. So in this case, you are going to apply the first method, and that is to factor the radicand into perfect and non-perfect nth power. So therefore, we have the eighth root of a raised to 16 times the eighth root of 9a raised to 6. As you can see, the eighth root of a raised to 16, 8, which is our index, and 16 are multiples. So therefore, we can reduce this first radical expression, while the second factor or the second radical expression, eighth root of 9a raised to 6, note that 9 could be written as 3 squared. Since 6 and 8 has a common factor, and 9 could be written as 3 squared, so therefore 2, 6, and 8 has a common factor, so that means we can reduce our index 8 into its lowest possible order. So therefore, we have a square times the fourth root of the square root of 3 squared a raised to 6. Take note that if we are going to multiply the indices, we have 4 times 2, so we have 8. So simplifying the inner radical by applying the laws on radicals, therefore we have a square times the fourth root of 3a raised to 3. So as you can see, our radical expression is already in its simplest form. Third method is to rationalize the denominator of the radicand. In rationalizing the denominator of the radicand, we can remove the radical sign of the denominator by making the radicand non-fractional or simply multiply both the numerator and the denominator by a quantity to make the denominator a perfect power of the index. So take note, rationalization is the process of removing the radical sign in the denominator. Example, we have to simplify the square root of 3/5 by making the radicand integral. So we need to rationalize our denominator. So how are we going to do that? We need to multiply our denominator by a radical expression that would make our denominator a perfect square, since our index in the expression, in the rational expression, is 2. So we need to multiply both the numerator and the denominator by the square root of 5. So therefore, we have the square root of 3/5 times the square root of 5 over 5. So that makes us have the square root of 15 over 5 square. So therefore, we have the square root of 15 over 5. Another example, we have to simplify 10 times the square root of x squared over 12. So we are going to assume that x is greater than 0. What are we going to multiply to the expression such that our denominator, which is the square root of 12, will become a perfect square? Yes, we need to multiply both the numerator and then the denominator by the square root of 3. Since 12 times 3 is equal to 36, and 36 is a perfect square. That means we can write 36 as 6 square. So therefore, we have 10 is equal to the square root of 3x squared over 36. So we are going to apply the first method in simplifying the numerator, while we are going to apply the first law of radicals in the denominator. So therefore, we are going to factor our radicand into perfect and non-perfect nth power, particularly the numerator, while the denominator, we can write it as an exponential expression. So therefore, we have 10 times the square root of x squared times the square root of 3 over the square root of 6 squared. So by applying the laws on radicals, therefore we have 10x, because the square root of x squared is x, so we have 10x times the square root of 3 over the square root of 6 squared, which is 6. Since 10 and 6 has a common factor, that means we can reduce 10 over 6. So therefore, we have 5x square root of 3 over 3. Next example, rationalize the denominator of the square root of 8a over 3bc. So what are we going to multiply to the numerator and denominator such that our denominator would become a perfect nth power? We are going to multiply both the numerator and then the denominator by the square root of 3bc. Therefore, we have 8a times 3bc is 24abc, while 3bc times 3bc is equal to 3 squared, b squared, c squared. Therefore, we have the square root of 24abc times 3 squared, b squared, c squared. So we can simplify our radicand. Taking into consideration the numerator, we have square root of 24abc. We can factor this into perfect and non-perfect nth power, while the denominator over 3 squared b squared c squared, we simply use the law on radicals. So therefore, we have the square root of 4 times the square root of 6abc over the square root of 3 squared b squared c squared. So the square root of 4 is 2. while the square root of 6abc is already in its simplest form, so we are just going to copy this. While the denominator, we simply canceled out the index as well as the exponent, since the exponent 2 is equal to the index. So therefore, we have 2 square root of 6abc over 3abc. Let us have an activity. Simplify, assume that the variables are positive. So in answering this activity, you pause this video for you to have an ample time to solve. After which, you can play and see if your answers are correct. So for number 1, square root of 16. So this one is equal to 4. Since 16 is a perfect square, so it is easy for us to identify its square root. Next is the square root of 180. 180 has a perfect square factor, and that is, yes, so therefore we have square root of 36. 36 is the highest or the greatest perfect square factor of 180. Multiply it by 5. So in other words, we are going to factor 180 into perfect and non-perfect nth power. So therefore, we have 6 square root of 5. Next, we have the fifth root of 486. So we need to determine the factor of 486, which could be raised or which could be written as a power of 5. And that factor is, yes, that factor is 243. So we are going to factor the fifth root of 486 as the fifth root of 243 times the fifth root of 2. So therefore, we have the fifth root of 3 raised to 5 times 2. Since 243 could be written as a power of 5, which is 3 raised to 5. So therefore, we have 3 times the fifth root of 2. Next, we have the square root of 4x squared y cubed. Again, we are going to factor the square root of 4x squared y cubed into perfect and non-perfect nth power. So therefore, we have the square root of 4x squared y squared times y. So therefore, we have 2xy times the square root of y. Since 289 is a perfect square, while a raised to 4 and b raised to 2, the exponents of a and b, our radicands, is a multiple of our index, we can simply apply the first law on radicals. So therefore, we have 17a squared b. Next is root of 128, x raised to 5, y raised to 4, z raised to 3. Again, we are going to factor the radicand into perfect and non-perfect nth power. Since our index is 3, we need to identify the factor of 128, which is a perfect cube. While for the variables x, y, and z, we need to get the highest multiple of 3 from those exponents. So therefore, we have the cube root of 64, x cubed, y cubed, z cubed, times the cube root of 2x squared y. So the first factor is a perfect nth power, while the second one is non-perfect. Therefore, by applying the laws of radicals, we have 4xyz times the cube root of 2x squared y. Next, we have the square root of 54x cubed yz. So what is the perfect square factors of 54? Yes, we have 9. How about x cubed? Is 3 a multiple of our index? It is not. But what is the highest multiple of 2, our index, which we could derive from the exponent 3? Yes, we have 2. While 6, the exponent of our radicand y, is a multiple of our index 2. So therefore, we have the square root of 9x squared y raised to 6 times the square root of 6x. So therefore, we have 3x y cubed times the square root of 6x. Next, we have the square root of 200ab squared. So we are going to factor it as the square root of 100b squared times the square root of 2a, which lead us to 10b times the square root of 2a. The square root of 64a raised to 6b. Yes, we are going to factor it as the square root of 64a raised to 6 times b, which leads us again to 8a cubed times the square root of b. We have the square root of 7a over 9b. So we need to rationalize our denominator by multiplying both the numerator and then the denominator by the square root of b. Therefore, we have square root of 7ab over 9b squared. So that leads us to square root of 7ab over 3b. We have the fourth root of 162x squared y raised to 4 z raised to 6. Therefore, we have the fourth root of 81 y raised to 4 z raised to 4 times the fourth root of 2x squared y squared. So therefore, we have 3yz, fourth root of 2x squared y squared. Next is we have the cube root of 1/9. So we need to rationalize our denominator by multiplying the numerator and then the denominator by the cube root of 3 over 3. So therefore, we have the cube root of 3 over 27, which gives us cube root of 3 over 3. Next is we have 2/5 times the cube root of 5 over 2. So we need to rationalize again our denominator by multiplying the numerator and then the denominator by the cube root of 4 or the cube root of 2 square. So this will lead us to 2/5 times the cube root of 20 over 2 cubed, which is equal to 2/5 times the cube root of 20 over 2. So therefore, multiply the numerator and then the denominator, which gives us 2 times the cube root of 20 over 10, 2/10, 2 and 10. The coefficient 2 and our denominator 10 could be simplified as 1/5. So therefore, we have cube root of 20 over 5. And lastly, we have the cube root of x cubed over 12. So what are we going to multiply to the cube root of 12 so that it would become a perfect cube? Yes, we need to multiply it by the cube root of 12 square or by the cube root of 144. So 144 x cubed over cube root of 12 times the cube root of 12 square. So that is the cube root of 12 cubed. So therefore, we have x times the cube root of 144 over 144 has a perfect cube factor, so therefore we can still simplify our numerator as x times the cube root of 8 times 18, since 8 is a perfect cube, which is a factor of 144. So therefore, we have 2x times the cube root of 18 over 12. Again, 2, our coefficient, and the denominator 12 could be simplified since they have a common factor, which is 2. So therefore, we have x cube root of 18 over 6 as our final answer. So did you get the answers correctly? If yes, well done. But if not, you can play again this video and rewatch the lesson. So that's all for today. Thank you and God bless. Happy learning!